We left off here in this equilibrium chapter is obviously we're doing ice tables and ice table calculations. So remember, the ice table is important. A couple parts of it, definitely the change part is really an important part of it, and making sure that you do take the coefficients in the equation. And again, you a lot of times will have the initial molarity of each of the reactants, and a good number of times you will maybe not have anything for products. So remember, we could always assume 0 to start with. We got our minus 2x and our minus 3x and our plus 2x. In this case, because we were not given anything about the products, we can safely assume that we are going in that direction. Also, we saw an example, and it does happen occasionally, that you are given everybody's information. So remember, that's a point where you really do want to calculate Q, which is basically calculated the same way as K. It's our products over our reactants in that case as well. Just to verify, I would assume if it is this type of problem, you're not at equilibrium. Otherwise, there wouldn't be much of a problem for you to solve. But just to verify which way it's sort of heading, to reach equilibrium. And again, as we talked about, you obviously cannot calculate Q unless you have everybody's concentration. So that's sort of the key to know when you should do that. Obviously, we would carry this stuff down here. And this would go into our equilibrium expression, which once again is our product. So in my made up bad example here, it looks like some scary math. We will do this. So basically, we're just going to put these guys into here and solve for x. And x represents the change. X is all the x's, obviously, in this table here that we would need. So we did several examples last time in our big day of ice tables, and we did several ways to solve these. And there are different ways to solve it, as we talked about. Remember that, if you do have sort of like a perfect square situation, which sometimes does occur, then you could obviously do that, and it's obviously much easier on the math. If you don't, a lot of times you will end up in, again, that sort of quadratic situation here, where you do need to use our quadratic formula to solve it. As we talked about and as we saw, again, you will end up with two different answers. And again, those answers could both be positive. They both could be negative. It could have a positive and a negative one. The way you could sort of eliminate, obviously, the incorrect one would be when you would go back into your equilibrium line, for example. It will yield you a negative concentration or pressure. So obviously, you cannot do that. Lastly, in a situation where maybe you do get some scary math, hopefully, if your K value is small, you can try the assumption and assume that x is equal to 0. Remember that when we assume that x is equal to 0 in this case, it is only the x's that we are subtracting from a particular number, or maybe adding to a number. It is not like the x by itself, like 2x would be in this example here. You got to leave one x to solve for, and that's the one that you would leave to solve for. The purpose and the reason why we can do that is if we have a small value of K, that means that when we do reach equilibrium, we should mainly have reactants. And because we would mainly have reactants, the change part of our ice table should be relatively small. So there shouldn't be a lot of reactants going to products. And we could assume that it's almost negligible, the amount of change that's going to occur in that case. And that is why you could only do the assumption when it is a small value of K. If you have a large value of K, it means basically the complete opposite. It means that when you reach equilibrium, you mainly have products there. And because you would mainly have products, that means the change from reactants to products should be relatively large and not negligible. So that is why, again, we didn't use, say, the assumption there. On our earlier problems when we had, K values of like 54 or 7 and things like that, because they're really large. Whenever, though, that you do an assumption, you do need to check it. And again, we will use, like I said, the 5% rule. And basically, to check your assumption, you take the X value you got, You divide it by the number you were going to either subtract or add it to, and times it by 100%. Yeah. So basically X value you get when you solve it, divided by the number, again, either you're going to subtract or add it from, and times it by 100. And if it's 5% or less, then you're good. That's considered negligible enough there, not a big enough change. Again, if it happens to be over 5%, you then need to go back and solve it some other way. And again, for us, that would probably be the quadratic formula that you could do. So it does bring up an option for you as you're doing these problems that if you do the assumption in certain situations, obviously it could save you some time. But if it ends up not working, you got to go back and do it anyways. Just so we're clear, you don't have to do the assumption. You can just work it out quadratic formula ways. If you just love that formula and want to do it, you can just roll with it and kind of work it out that way. Again, it should come out the same. But obviously, if you do the assumption, it will maybe save you some time along the way. The other and last thing that we saw as well is, again, a lot of times we'll do ice tables with concentrations, but really you could do it with any type of unit. And we could use our Kp value and pressure and do it. And as we talked about, again, if you are going to do an ice table involving pressure, once again, it does need to be in atmospheres when it goes into the ice table and you do the calculation part, and then you can convert it to some other unit, afterwards. Any question on any of that ice table stuff, calculations? Clearly, this is, as I might have mentioned, the calculation of the semester. Yes, so this is like the deal here. You'll be doing ice tables every time you have to do a calculation, pretty much. Any questions on any part of those calculations? Yeah. All right, so we're going to then finish up sort of the last part of this chapter on equilibrium, which is the Chatlier's principle. And as I mentioned, it also is sort of the part of the lab we're going to tackle here today. So basically the idea here is when we're talking about Le Chatelier's principle is we have a system that's basically at equilibrium. So we have this system that has basically reached equilibrium. So, we'll call it like A plus B goes to C plus D. And this is like equilibrium position 1. Now, as we talked about, when a system reaches equilibrium, basically what that means is the rate of the forward reaction will equal the rate of the reverse reaction. So once this thing reaches equilibrium, we have those rates that are basically equal to each other. And basically everybody's sort of happy and arranged nicely. As we talked about, once again, it doesn't mean that we have the same amount of everybody on each side, but when it does reach equilibrium, whatever their concentrations are, if you're looking at pressures, whatever their pressures would be, they basically get locked into place. So there's not much changing in terms of their concentration because as it goes forward, it'll go backwards at the same rate. Now, you could do something to a system that is at equilibrium and is sometimes referred to as adding a stress. So you could add a stress to the system. And frankly, when you will add the stress to the system, you will screw up the equilibrium. So it will no longer be at equilibrium. It was nice and happy going back and forth at the same rate, but you decided, hey, I'm not happy with that. I want to do something to it. So you could add a stress to a system at equilibrium. Some of the ways that we could add stresses that we'll talk about is you could do something with the concentration of either reactants or products. You could do something with like the pressure or volume. If you're dealing with gases, you could do something with the temperature. And, you could also maybe add a catalyst, which, don't do very much as we'll talk about, but, sometimes included here as well. So you have this system that's at equilibrium. You do something to stress it out. It is no longer at equilibrium. One of the sort of nice things about these reversible reactions is, frankly, they want to return to a state of equilibrium. So even if you kind of screw it up, it wants to find its way back to that equilibrium state. And that's what's going to happen. So the system above there is going to be kind of screwed up by you doing something to it. It's going to want to return to equilibrium. And there's really, I guess I'll say three. There's really three things that could happen in a situation when you add a stress to a system that's at equilibrium. In order for it to be able to return to equilibrium, it may have to shift to the right, which basically means we need more products to return to equilibrium. It may require this reaction to, as it's referred to, shift to the left, which obviously would mean that we need to make more reactants. And there are certain stresses that do occur, and in certain situations, even though you may have added a stress to it, it's not going to really do much. It's not going to shift either way. So there can be no change that could occur as a result of something that you did to it as well. I would say in most cases, you're probably going to see one of those two things occur. Either it's going to go to the left, go to the right. But again, there are a couple of instances when you could do something to it and it really will not cause any change. So as the reaction sort of readjusts itself from the stress that you added, what will happen is it will once again, all right, up here on top, it will once again return to this equilibrium state. And this would be sort of like equilibrium position number 2. So that's sort of the idea of the Chatlier's principle. You have this nice system at equilibrium, something occurs to it, you do something to it, somebody does something to it, stresses it out, messes up the equilibrium, so we're no longer going back and forth at the same rate. The actual reaction will adjust in a way to either go to the right to make more products to reach equilibrium again, go to the left to make more reactants to reach equilibrium again, and then it will come back to equilibrium position. Will it end up with the same amount of reactants and products as it started with? The answer is maybe not. But what it will, in most cases, there is an exception here, but in most cases, what it will do is it once again will return back to the same proportion of products to reactants, which will give you the same equilibrium constant value. Once again, here we'll talk about temperature. Temperature, again, is the only thing that will not get you back to the same equilibrium constant value. But all the other ones will get you back to the same sort of products over reactants. And as we talked about, the idea of equilibrium is you could start at different positions and really end up with the same equilibrium constant value. And the idea behind that is as long as you don't change the temperature, the equilibrium constant value will be the same. So like my simple math thing of, you know, if you take 4 divided by 2 is 2, right? Take 8 divided by 4 is 2. So there's many different ways that if you do the math part and divide different numbers, you'll get the same result. And that's sort of what happens here. The products and the reactants end up at the same proportions and end up at the same equilibrium constant value, again, as long as you do not change the temperature. Any questions on any of that there? So let's talk about some of the things here that we could do and sort of the effect that it has. So we'll start with concentration. Pretty much concentration, there's two things you could do. You could either add more. What I mean by that is you could either add more products, you could add more reactants. When you add more, it will shift away from the side you added it to. Now, the other thing that you could do is you could remove some reactants, you can remove some products, and when you remove, it will shift towards the side you removed from. So adding more is pretty simple, right? If you want to add more reactants or products, frankly, in most cases, like you'll do today, you just go grab a bottle and dump it into your beaker, right? Or your test tube or whatever it is. It's pretty simple. You can just reach right in there and grab a bottle and dump it in. When we want to remove something from a system at equilibrium, let's say in our test tube or our beaker, do we reach in and just grab it out with our hand? I hope not. That seems like a very bad idea, by the way. You should not do that, right? So if I have a solution, how can I remove something from the solution? Ask it nicely to leave. Yeah. So really, when we think about equilibrium, right, there are really two things that we do not include in the equilibrium expression, right? One thing that we do not include in the equilibrium expression is things that are solids, right? And things that are pure liquids. So as was said there, we could add something to our solution that will basically form a precipitate. In order to form a precipitate in our solution, right, there's a whole bunch of ions floating around. When we add something in, one of the ions that we added in and when the ions float around will come together based on solubility rules, right, and drop out of solution. As that ion that was originally in the solution floating around gets dropped out of solution, that is essentially like reaching in and taking out that ion or whatever it may be. So forming a precipitate is a very common way that we could kind of reach in and take out something from a solution. And that is something actually that you can visually see, right? You can visually see that you made a solid. So that's a pretty easy one. The other way that we could do it is something that maybe is not so visual, that we can't visually see occur. And that is oftentimes the formation of water. So how you doing? When we make water, that is one way that we can remove something like hydroxide or H plus from a solution. So if we have some type of equilibrium that has OH minus or H plus in it, and we add either an acid or a base, depending on the situation, the H plus and the OH minus will come together and that will make water, which is a liquid, right? And that also would not be included in equilibrium. And that is a way we could remove hydroxide or H plus from a system that's in equilibrium. Although you may not be able to visually see that occur, that is sort of what is happening, and you'll be able to perhaps see the shift in equilibrium that would occur. So those are really two very common ways, and how you'll do it in this lab as well is to remove things from a solution is either make a precipitate, which is a solid, or make something like water, which would be removing H plus or OH minus. Any questions to that there? So if we do some award-winning drawing here, a little stick figure action. By the way, this is advanced stick figures because there are faces that are on here as well. There you go. It's the advanced class. The regular class is just the body, no face, but you know, you get the eyes. So this is the reactant side. That's the product side. And let's say that we decided we're going to add some more products. So we throw somebody here on our teeter-totter, and we pop guy there. And this guy goes like this. Not so happy. Now to fix this, if this was really our equilibrium position number one, we would need to put more people on the right-hand side or left-hand side. We would need to put more people on the left-hand side, right? So we add it to the right, it shifts away from the side that we added it to. We would need to put more people on the left-hand side to once again return to equilibrium here. As well. So this is sort of what happens. Once again, we're going to return to equilibrium position number two. Again, maybe not the same amount of reactants and products that we started with, but the ratio again here would be the same for our equilibrium constant as long as we didn't change the temperature in addition to doing that. Now, let's say we have the same sort of equilibrium happening here. Once again, this is our reactant side, this is our product side, and we're at equilibrium number one here. This guy decides I'm going to hop off, so we're going to remove that side. What's going to happen is we're going to get this situation here where basically this guy again is not so happy on that side. To fix it, we need to put more people back to the right-hand side in this case. So we remove from the right-hand side, it will cause it to shift to the right-hand side. And once again, it will be able to return back to equilibrium position at this point. Any questions on that there? Okay, so that's the deal with concentration. Add away is a good way to remember it. AA, add away. And obviously when you remove, it goes towards the side. Now, when we talk about shifting to the right, shifting to the left, right-hand side, left-hand side, clearly when we put all that into our beaker, there's not like a left-hand side, right-hand side of our beaker, right? They don't just go, I'm going to stay on our sides or anything like that. So obviously everything's flown around. So when we're talking about obviously right-hand side, left-hand side, we are referring to the equation, right? So the reactants and the products is basically what we're referring to when we talk about sort of shifting to the right, shifting left, or adding to the right or adding to the left. The other sort of thing that could happen is pressure and volume, which are oftentimes sort of linked together. And that is because there is a relationship right between our friend's pressure and volume, our friend Boyle's law, perhaps. Yeah. As pressure goes up, what happens to the volume? It does go down. Yep, 50-50 shot on that. I like it. There we go. So as the pressure goes up, volume goes down. The reason the pressure goes up, right, is the volume goes down, which means all the gas molecules are in a very small volume, which means that increases the rate of collisions. The increase in the rate of collisions is why we see an increase in the pressure that occurs. Then obviously the opposite is true here. If the pressure goes down, that typically is a result of the volume going up. So once again, if the volume increases, it gives all the gas molecules a lot more room to fly around in. Also means that their number of collisions will start to come down, and then we will see the pressure start to come down as well. So when we do these situations, when pressure and volume are sort of hooked together like this, a lot of times it's sort of best to think about the volume aspect of it. And what I mean by that is, if the pressure starts to increase in this situation, because frankly, the volume got really small or got small, would we need more or less gas molecules to fix that change that occurs? So really the change that's occurring, right, is the pressure starting to rise. So if I want to kind of bring the pressure sort of back down, would I need more or less gas molecules in that small volume? You would need less gas molecules in that small volume. If you put more gas molecules in that small volume, you're going to continue to see the pressure increase, right? So the change that's occurring here when we're stressing the system out by shrinking the volume is we're starting to see the pressure start to rise. So to fix that, we kind of want to bring the pressure back down. And in order to do that, because the volume is smaller, it would shift to the side with the least number of gas molecules. Now, clearly that is reaction dependent as to which side has more or less gas molecules. Obviously, we would be looking for anybody in the reaction with cheese next to their names or symbols, and we would basically just count up the coefficients, right? It's an easy way to figure out how many got going on there. Opposite is true here. If we sort of increase that volume, the change that we're going to see is the pressure is going to start to drop. So we kind of want to bring the pressure back up to kind of fix that change that occurred. So in this larger volume, we would need a lot more gas molecules to fill it up, because if we fill it up with a lot more gas molecules, we will then see an increase in the collisions, and we will see the pressure start to come back up. So this would then shift to the side with the most gas molecules. And once again, like I said, it really is sort of specific to the equation or the reaction that you're dealing with as to which side obviously has more or less. So personally, I usually, when I think about pressure and volume, tie them together. And in those situations, I think more about the volume. So really small volume, less gas molecules, larger volume, more gas molecules is a good way to remember that. So small, less, more, larger, more gas molecules. And that's a good way to kind of do that. Once again, here, changing the pressure, the volume will not affect the value of the equilibrium constant. Again, we'll end up with sort of the same ratio of products to reactants in this case. Any questions on that there? All right, the next kind of big thing that you could do to a system that is at equilibrium is to play with the temperature. And pretty much temperature works the same way as concentration. So the change in temperature will really work the exact same way as concentration. And that means there's very much two things you could do. You can increase the temperature. And increasing the temperature means that it will shift away, just like it does in concentration. And if you decrease the temperature, that's like removing, and it will shift towards. So temperature works the same way as concentration. Increase goes away, reduce the temperature or decrease temperature goes towards it. But we need to sort of understand sort of which way that will cause the shift to occur. And really temperature is related to the type of reaction that you're dealing with in terms of energy. So there's really two types of reactions that we deal with. One is exothermic, which means our heat and energy is released. And endothermic, which means heat and energy is absorbed. So when we have an exothermic reaction such as this, we consider heat to be a reactant or a product, although it's not correct in all aspects, but if it's exothermic, should we consider the heat or energy to be a reactant or a product in this case? It should be a product. It's being released or given off. So we oftentimes think of heat as a product in an exothermic reaction. And the opposite is true when we have an endothermic reaction. Heat and energy is being absorbed. So we sort of think of heat and energy, again, not really correct in all aspects, but we typically do. We think of heat and energy as being a reactant, like it's being added to this reaction. In addition, in most ways that we can kind of determine if it's a exothermic or endothermic reaction is in most cases you're given a delta H value, right, which is our change in enthalpy. And if it's an exothermic reaction, delta H should be positive or negative. Should be 50-50 shot. Should be negative, yeah. So if you have a negative value for delta H, doesn't really matter the number, it's actually the sign that's most important. Pretty much with heat and energy, any value that's negative means it's an exothermic sort of process. Heat and energy is being given off. And obviously the opposite would be true for our endothermic guy. If we see a delta H value that's positive, it means it's an endothermic process. Overall heat and energy is being absorbed. Once again, doesn't matter really the number. It's actually the sign that's most important in this sort of situation. So what this means is if I have a exothermic reaction and I increase the temperature by putting it in hot water like you will do today, which way should it shift if I increase the temperature of an exothermic reaction? It should. So that's like left, right, upwards. So exothermic would be here. If I increase the temperature, I'd be like adding heat to our right-hand side, which means it will shift away and we should make more reactants in this case. If I decide to put it on ice, which you will also do today, right? Which way should it shift for an exothermic reaction? If I put it on ice, that is like removing heat and energy, which would be like removing products, which means it then should shift to the product side. The opposite would occur for an endothermic, right? If you increase the temperature of an endothermic reaction, you have heat on the left-hand side, it will shift to the right-hand side and you'll make more products. If you throw an endothermic reaction on ice, it will shift towards the left-hand side and you'll make more reactants. Yeah. So if you're given the delta H value, like I think you are, they give it to you these days in the experiment. Years ago, you had to figure it out yourself, but I think now they give it to you. And you know the delta H, then you should be able to predict which way it should shift when you add, put it on hot water, which is like increasing the energy and the heat, or if you put it on ice. By the way, if you didn't know, but you know some different colors of each side, right? One side makes red, the other side makes purple, whatever it may be. You can know by either adding hot water or ice to the system, and you can see which way it shifts, and you would be able to figure out, you know, is that reaction exothermic or endothermic based on which way it shifted when you did the hot water or cold water or ice sort of situation. So there's ways that you can actually in an experiment figure out, is that reaction exothermic or endothermic, if you weren't sure. So for example, if you had this, and this was say red color, and this side, when it went to this side, was purple, and you decided that when you put the test tube in hot water, it shifted and turned red. But then when you put the test tube in an ice bath, what happened was it turned purple. Do those things agree? And first off, what type of reaction would this be? Would this be exothermic or endothermic? So let's reason through this, shall we? Yes. All right. Let's start with the first observation we made. I put the test tubes in hot water. Like, that would mean, am I increasing temperature or decreasing? Increasing. And I saw it shift to the red hand side, right? So by increasing the temperature, I saw it shift this way. That tells me that when I increase the temperature, it should shift towards or away from where the heat is. Away, right? So in the order for it to shift to the left-hand side and turn red, that would mean that my heat would have to be a reactant or a product. It would have to be a product, right? Because I increased the temperature, it shifted away from it and made it red. Now let's see if my second observation agrees. I put the test tube on ice, which is like removing the heat and energy, right? And that should cause it to shift which way? Towards it or away? Should cause it to shift towards it, right? And that would mean, if that was correct for our first observation, we should see it shift to the right, which means our test tube should then turn, in this example, purple, which is what we saw. So both of those agree with each other, which they should if you observe these things correctly. So this is a way, just experimentally, if you weren't sure, you know, if it was exothermic or endothermic, you could do two very simple experiments. You actually only probably need to do one, but you can do two to verify, and they both should agree with each other, even though they gave different results, right? One gave red, one gave purple. But the idea behind what should happen when you increase or decrease the temperature allows you to understand, is it exothermic or endothermic? Any questions on that there? Yeah. Good news is they don't make you do that anymore. They just straight up tell you what it is. So I guess that's good, I suppose. All right, but we will do this actually today, and you'll hopefully see that it should agree, obviously, with what they tell you the type of reaction is. Any questions on temperature here? The last thing that we could kind of do to a system that's at equilibrium is add a catalyst. And as we talked about with catalyst in the previous chapter, really a catalyst is, again, not a reactant. It's not a product. And once again, it does not get used up in the reaction. It is there, as we talked about, in most cases to really just facilitate the reaction occurring faster. And as we talked about, it's able to do that by lowering the activation energy, right? So that hill that the reactants has to climb to get to the other side, and thus the reaction occurs faster. The good news on equilibrium is it has no change, really. So that is the one thing that you could do to a system that's at equilibrium. It will just get there quicker, but it will have no change on shifting left or shifting right. The other place where possible you could have no change is with gas molecules. You could have an equal number of gas molecules on both sides, and that will cause a no change to occur. By the way, we just talked about the temperature one, and once again, a reminder that it is the temperature that is the only thing that will change the numerical value of the equilibrium constant. And again, that is a change between two different temperatures. They will be different. So as we talked about before, if it's 25 versus 40 degrees, the value of K will be different between 25 and 40. But at 40 degrees, it will be the same no matter how many experiments you run. At 25 degrees, it will be the same at no matter how many experiments you run. But the comparison between the different temperatures will yield you a different value for the equilibrium constant. Any questions on Le Chatelier's principle? So let's try some here. Let's do 2A plus B goes to 4C. Let's do a delta H of negative 125 kilojoules. All right, so what will happen? Will it shift to the right, to the left, or no change? If I add more C, I remove B, I decrease the volume, I increase the temperature, I decrease the pressure, and I add a catalyst here. All right, so for each of those situations separately, what would we predict would happen to our equilibrium here? Would it shift to the left, shift to the right, or be no change? So take a minute, see what you come up with here. Okay, let's take a look here. So once again, we're going to add some C. That should make it shift which way? We're adding C, which is on the right-hand side. So when we add, it should shift away. So it should shift to the left. The reason why it should shift to the left is, frankly, we added more products, which means we're going to kick off the reverse reaction, right? It's going to have more products available to react with itself and make more reactants. So basically, we're initiating the reverse reaction to occur here. If we remove B, B is on the left-hand side. Get that correct, the left-hand side there. And that means that we should see it go which way? Should also go towards it, yeah? In this case, what happens when you remove B is we're removing reactants, which makes like a hole on the reactant side that then needs to be filled by the reverse reaction occurring to bring back up the concentration, basically. In this case, we're going to decrease the volume, which means it should shift which way in this case? It would also be to the left. So when we decrease the volume, we would expect the pressure to increase. So what we want to happen is to kind of bring the pressure back down. So since the volume is now smaller, it needs to go to the side that has the least number of gas molecules. And looking on the left-hand side, that is 2 and 1, which is 3 gas molecules. And that is 4 gas molecules, right? So we're going to shift here to the left-hand side. In this case, we're going to then increase the temperature. So we do have a delta H value given to us. I'll spit that out. Delta H value given to us means here in this case, endothermic or exothermic. It is exothermic because it's negative, which means if we added the heat to our reaction, it would be on the product side. And now we're increasing it, which means it should go to the left as well, right? Away. I just randomly picked apparently all left-hand side shifts there. So it won't always be the left, but in this case, we're adding some heat to the right-hand side. It will shift away and go to the left. Let's see, maybe I went the other way on this one. If we decrease the pressure, that means what happens to the volume? Volume gets larger, right? So then I need less or more gas molecules in that larger volume. More. In this case, it would then shift to the right. Hey, I found a right. That's good. And in this case, if I add a catalyst, it will be no change. Yeah. Any questions on any of that there? All right. All right. So this is the stuff we talked about. So I'll just kind of scroll through it basically. We'll take a look at a couple more here. Let's say we removed NH3, we decreased the temperature, and we'll do a delta H negative 325. We'll do this one. We'll do increase pressure. H2. And that's good, I think, for now. All right, left, right, no change. Okay, let's take a look. So we're going to remove some NH3. So NH3 is over here on our product side. So when we remove it, it should go which way? Should shift towards it, right? Once again, what we're essentially doing here is removing products, right? So once again, if you want to think about it, if you remove products, you created a hole, the reaction is going to realize that and then go try to fill back up the hole, right? To fill it, to fix it. So it's going to go towards that side and shift that way. If we decrease the temperature here, once again, we see a negative value for our delta H, which means this is going to be exothermic. So if I decrease the temperature, it will go which way? It's going to go towards the side where the heat is. So in this case, it would shift to the right. If I increase the pressure, once again, in terms of volume, my volume gets smaller, right? And by increasing the pressure, the volume is smaller. In this particular case, it should shift which way? Should shift this side with more or less gas molecules? Which side has less? The right. So clearly on this one, I picked all rights. The last one was all left. If we add some H2, it's going to go. Oh, might as well go to the right since I clearly picked them all that going that way. So we are adding more reactants. What that's going to do essentially in terms of the reactants is increase the reactants. And that's going to basically allow the forward reaction to kick off. And then again, that's why we're going to see more products being formed in that particular case. Any questions on those there? Okay. All right, last one here. Let's do increase the pressure. Let's do increase the temperature. Let's move NO, and we'll add some O2. All right. Okay, so on the first one here, we're going to increase the pressure. So once again, pressure, volume sort of related to each other. So if we increase the pressure, volume should be large or small? Should be small. So it should shift to the side with more or less gas molecules. And which side is that in this case? That is actually neither in this case. Left-hand side, there's 2 gas molecules, right? Right-hand side, there's 2 gas molecules. We call that a tie, which would then be a no change situation. So this is another place where a no change could kind of pop in based on that. Increase the temperature here. Which way will it shift? It will shift to the right. I know that because endothermic, which means heat would be over here. If I increase to the left, it will shift away. Once again, I'm going to increase the forward reaction occurring in this particular case. If I remove if I remove NO, there we go. That's going to make it shift to the right. Again, NO is over here. So once again, we're depleting or lowering the amount of products. Again, the reaction is going to want to kind of fill that hole, and it's going to kick off the forward reaction to do so. And lastly here, adding O2 will basically increase our reactants, which then should increase the forward direction of the reaction occurring and heading to the right there.